Professor Santo, Fortunato is one of the main people in this field. So kind of the Mick Jagger of complex networks. He's a rock star.
And I can probably put this here. Can you hear me?
Yes.
Yeah? Even if I raise my head like this? Yeah? Good. It's in the back? Thank you. Yeah, let's make sure there are no interferences. So thanks everybody. Thanks for being here. Thanks to the organizers for bringing me here. My first time in Toronto. So thanks Pierre, for giving me the opportunity. Thanks to my friend Mario, where actually, eventually I know this is between a discussion between the two of you that eventually had the idea to invite me here. So I suppose it's not a coincidence that the web talks about community detection before me, right? Because it's probably I know one or two things about the topic. In fact, I almost finished my book after 9 years and 840 pages, but I'm going to squeeze a little bit. It's going to be probably no more than 600. So you're going to see it next year out. It's going to be called Network Community Detection. Today I'm going to tell something about this. However, I thought that for your sake, it would be probably better to talk about something really shocking we found 2 years ago, which explains the title, which eventually, again, after thinking everything is obvious once you know the answer, right? The book by Duncan Watson. So, but at the beginning it was really shocking, and I tried to present it to you as a shocking thing until I tried to give some explanation. And by the way, this is work in progress. I mean, after 2 years, despite, of course, with multiple interruptions and stopping points and so on, we are busy with doing many other things. Plus, one of the collaborators moved to a different university, so these things don't help to coalesce. There are still a couple of loose ends, and in fact, I can offer co-authorship to whoever of you, comes up with a better explanation than the one I have, and I'm going to offer, because I don't have a really rigorous argument to explain what happened. However, it's such a general thing that there must be a simple reason behind it. So that's a mystery. So what am I talking about? Let me see if I can do it from here. So first of all, let me thank, of course, the 4 people that, besides me, are involved in this. Felipe Silva, Salamoy Koyako is the one who's now in another university, SUNY Binghamton, Alessandro Flamini and Filippo Radicchi from Indiana University, Bloomington. So this is a network, it's an event about economic networks and so on. But even without that, I like to start with this example to give you a sense of what I mean, and hopefully to make a striking case for this property that I call scale invariance, that you can call however you like. I'm going to define the term now, and if the semantic doesn't square, please forgive me, which is a world trade network. So of course, I don't need to tell you what it is. A country is exchanging goods. So the nodes are the countries, and the edges are trade flows between countries. And the unit of edge weights is the currency that you use to quantify these exchanges. So it could be dollars, yuan, euro, anything you want. Now, suppose that I use 2 different currencies to quantify these exchanges. So the only thing I need, I just change the currency, right? I use dollars on the left, say, I don't know, yuan on the right. But any 2 currencies you want, pesos, whatever you like. And here's my question for you, which is a question I ask myself. Do you think that the properties of the networks of 1 and 2, and the conclusion of any analysis running on them, depend on the specific currency adopted? Yes or no?
Yes.
Do you think it depends? So it should be independent. Okay. Sorry?
What do you mean by adopting the currency?
Well, I mean, you need to weigh, you need to measure these exchanges, right? I mean.
You're just talking about the weight.
Yeah. No, I mean, but of course it changes the number. I mean, if I measure how many goods go from the United States to Venezuela, probably not many, good bad example. Let's say Ecuador, or maybe Uruguay, or Italy. You can weigh them in many different ways. You can use euros, you can use dollars. The number, I mean, the quantity is the same. You're just using a different unit. So it's a choice of the unit. So the question is, do you think that any conclusion, I'm not talking about the raw numbers. The raw numbers, of course, are going to change. You multiply by a number, then, of course, the number is going to change. If it's a big number, it's going to be a big number at the end. If it's a low number, it's going to be a low number. You can always divide. You cannot talk about millions of dollars or thousands of dollars. So even within the same currency, you can also change the scale, right? You can talk about cents or thousands of dollars, hundreds of dollars, millions of dollars, billions of dollars. It depends. And sometimes, of course, you choose the unit as it is convenient also to represent things nicely in a plot or diagram. So I think we probably agree, and please tell me if there is an outlier or more, that the result should not depend on the choice of, please.
So, but the value of the currency itself depends on the strength, depends on the flow. Like if you increase the demand for goods from a certain country, then the currency will go up. I don't know.
No, I mean, we're not talking about dynamic here. We're talking about, suppose that we have the exact exchange today, right? Or, any day. And I just do the switch. I just convert one thing to the other. I'm just talking about multiplying things by a number. Okay? Like I say, you don't even need, like I said the example before, you don't even need to talk about different currencies. You can take the same currencies, like, the US dollars, and then you say thousands of dollars, hundreds of dollars, millions of dollars. It gives you a different number, of course. But all the numbers are rescaled by the same number, which is a scale factor. Okay? That's what I'm talking about. Yes? There was some, oh, sorry.
Central bank policy is going to differ across countries. The liquidity characteristics of different currency markets are going to differ. I think the burden of proof is on you to argue that these things should not be different.
Yeah, exactly. And in fact, that's the reason why we're building this, right? And because, I think it's fairly intuitive, and I'm going to quantify now outside of the economic context, that the results should not change. I'm talking about really like distributions, rankings, centrality measures up to a scale. So that's exactly what I mean by scale invariant. Suppose that I have then a weight matrix, which could be the weight matrix indicating the exchanges of goods between the countries, but it could be any weight matrix of any weighted network. And they indicate with the letter capital W. This thing should work. Yeah. And suppose that I multiply all the weights by constant A, positive. Oh, actually, it's working now. Okay, interesting. So, so how do quantities change because of that? Suppose that we take the strength, which is the weighted degree, right? The sum of the weights of the edges connected to the node, which is a natural extension, the natural extension of the constant of degree in the case of weighted graph. So it's just the sum of the weights of the edges ij, where j is a neighbor of I. If I multiply everything by A, then of course at the end the strengths are going to be multiplied by A, because it's a linear function of the weights. So that's simple. However, neither the distribution of the strengths nor the ranking of the strengths is going to change, right? The node with the largest strength is going to be the same regardless of the specific value of A that I choose to do this multiplication. And the same thing for the distribution, because I'm just inflating everything by a constant. Let me give another example. The weighted clustering coefficient. I would say D, but in fact, this is one of those notions that can be changed. They're not uniquely defined. The first notion was proposed in 2004 by Barra, Barthelemy, Pastosadoras, Vespignani in a famous PNAS article. But that's not good in our case, and if you want, in our case, in any case, because what happens is that if the network is fully connected, which can happen, and it's still meaningful if you have a heterogeneous distribution of the weights, then that weighted clustering coefficient is always equal to 1. So, which is just not, it's something to realize a couple of weeks ago, though, that the thing has been out there for 20 years. So we use this other notion, which instead depends only on the distribution of the weights. It was proposed by Saramaki et al. In 2007, and this the way it reads. So this is the degree of node I. The clustering coefficient is a local measure. Then, of course, you can average it over all the nodes. And the Wij and Ik, Jk, of course, what closes a triangle. So if this form a triangle, Ij and K form a triangle, these three terms would be non-zero. These would be the weights. You multiply them by each other, you take the cubic root of that, and you divide by the maximum weight over all the edges. So the largest value of the weight. So that basically each of this ratio, Wij divided by W max to the power 1/3, cannot be bigger than 1. But again, here, if I multiply everything by A, like in this case, then of course I get A cubed here because of the three factors here and A here, but then there is a cubic root here and I get Ci. So in this case, you get the exact same weighted clustering coefficient, which is good, right? That's matches the intuition. The result should not change with respect to a change of scale. Final example, well, not exactly final, but this introduction, the weighted eigenvector centrality, which is basically the value of the entry, so the principal eigenvector of the weight matrix of the network. So this would be the expression here. This would be the eigenvalue. You take the largest eigenvalue, but if I multiply W by A, so I replace W with W prime here, and this would be then the same equation for this matrix here. Because of the scaling relation, you see that every eigenvector of W is also an eigenvector of W prime, and vice versa. The only thing that changes is the value of the eigenvalue, but the components are the same, entry by entry, once you normalize the vectors. So the eigenvector centrality is the same. I mean, if you normalize the vectors, of course. Otherwise, the same up to a scale. Now, the problem that we found has to do with something a bit more refined that a lot of network scientists don't do, making a big mistake, in my opinion, which is the assessment of the significance of their results, including a lot of people doing clustering, by the way, community detection. What do I mean by that? I mean comparing what I measure on the network with what I measure on a null model that generates some form of randomization of the network, preserving some of the properties of the network. So basically what you have your measure, it could be the clustering coefficient, it could be anything else, I don't know, page rank and so on. But you want to see if this measure is something very specific of that network, or it can be found, or is compatible with the same results you will find if you measure the same thing on a randomized network which preserves some of the properties of the original network. I mean, how you do it, you just create this randomization according to some recipes, and I'm going to give you a couple here, and you derive a distribution, should be your baseline distribution, and then you compute the p-value or the z-score of this, of the value that you measure on your network, initial network. And if the value is sufficiently small, then you say that, that the value is significant. For p-value, for instance, this is the null model distribution, and this is what you measure on your data set, on your initial network. Before the randomization, this would be the p-value, basically the area of this curve here. This is something you're probably already very familiar with, right? It's used everywhere in statistics and pretty much in all disciplines. Not so much in network science, and that's a mistake. And that's probably actually one of the reasons why this problem that I'm going to expose in a few minutes has not been found before, although there is evidence that people have the intuition that the specific null model that people have been using for so many years could give rise to this type of problem. So let's talk about null models. So what are good models that we can use to compare our network with a baseline? What kind of good baselines can we propose? There are, of course, many options, and there's been a lot of studies, some of them rigorous, some of them less rigorous, about ways to do that. And by far, the most famous way to do it is to do the so-called degree-preserving randomization, which basically means replacing the edges, but such that each node preserves the number of neighbors before and after the randomization. Now, this can be done exactly, or this can be done in expectation. If you do it exactly, which is a configuration model I'm going to talk about, it's going to be the main star of this talk, then we're talking about the microcanonical ensemble, because then you have a fixed number of units, and you respect things really strictly. The constraints are strict. And the other one is the canonical version, or also called Chung-Lu model, in which instead the degrees are preserved only in expectation. So if you average over many randomization, then you will see that the degrees are approximately the same as in the initial network, node by node. So the first one is the configuration model, the second one is the Chung-Lu model. You will see Chung-Lu sometimes as a label of some of our figures because we use the Chung-Lu model for convenience. The two ensembles are equivalent, like in thermodynamics, a microcanonical and a canonical ensemble. If you do studies that are large, an infinite volume limit, in the limit of infinite size, at the population level, nothing really changes. So, but we did it also with the configuration model, and of course the results are the same. So what is, oh sorry, let's confirm your speaking language. I'm pretty sure I'm talking English, please. Okay, no, it's okay. So let's talk about configuration model. It's been introduced many years ago. It's a classic thing used by everybody. In this case, each vertex has the same degree as in the original network. And the way to do it is a very efficient, very simple procedure in which basically what you do, if you have a degree sequence, for instance, I wanted this node, there's 2 neighbors, this node, there's 1 neighbor, this node, there's 3 neighbors, and so on. What I do, I just basically attach as many stubs as the degree that I want to have for each node, and then I close my eyes and I combine pairs of stubs chosen at random. That's how you create configurations according to configuration model. Very simple routine, super fast, and this is, for instance, a possible result of this. Not the only one, because of course you can have many configurations this way with equal probability. Now, one thing that is perhaps less known is that the probability that I and j are connected in the configuration model, if the nodes of the degrees I and j are ki and kj, is ki kj divided by 2m, m being the number of edges of the whole network. That's valid only when this ratio is very small. So, and for instance, Diego Galaschelli has proposed the exact way of implementing the configuration model, which involves a set of self-consistent equations and not a simple expression like this. But these expressions converge to this one when this ratio is sufficiently small. Now, based on what I told you, of course, if you just combine any pairs of stubs at random, you can also happen to pick 2 stubs attached to the same node. In this case, you close the loop. You have a link starting from a node and coming back to the node that will be called a self-loop. But you can also have multiple edges, because you can take multiple pairs of nodes attached to the same pair of nodes, of stubs attached to the same pair of nodes. In this case, you can have more than 1 edge. So these are things that you can get with the configuration model if you want to respect the probability distribution exactly. Normally, I neglect this configuration, which is not good practice, but I know that it's not going to change the values and the measurements that I'm going to make. More importantly than that, and that's the key feature of this whole thing, is that the distribution of the number of edges between any 2 nodes is Poissonian. So if you create many configurations and you take the same pair of nodes, you will see that the probability distribution of these 2 nodes having 0 edges, 1 edge, 2 edges, 3 edges, and so on is going to follow a nice Poissonian distribution. Just for, I don't know, I didn't know what kind of audience I'm facing, this is a Poisson distribution. And lambda is the average basically this number that I showed you before in the case of the configuration model. Because, and that's a nice thing, more than a probability, this is actually the expected number of edges that you have between I and j in the configuration model. And if you interpret it as an expected number of edges, it can also be bigger than 1, right? Because the mean of the Poissonian, the lambda, the characteristic parameter of the Poissonian, can be also bigger than 1, which means that in this case you may have multi-edges quite frequently. So actually, lambda is actually the expected number of edges between I and j. Again, it can be larger than 1. I'm this time trying to do like Agatha Christie and just putting the hints there, and then hopefully I'm going to be, but I don't know if I'm going to do a good job or not. You tell me at the end. Okay, so obviously, I'm giving a talk, so I had to say something about communities, but I'm not saying just because I had to do it, but because this is the way we found out about this problem. And that's why most of our results and most of our analysis revolved around this specific feature, which is called modularity, which is a score that is used to assess the quality of a partition. Samir knows actually how to optimize it exactly, and we're working together to propose a specific, more flexible version of the measure in which you can impose constraints on the sides of the clusters. You're going to see this paper soon. So just for, but since again, I didn't know exactly what I was facing, let me define the measure. This M is the number of edges, the total number of edges or links of the network. This is a sum of the clusters. MC is the number of links within cluster C, connecting pairs of nodes of cluster C, and the DC is the total degree of the nodes of cluster C, the sum of the degrees of the nodes of cluster C. And M is again a number of edges. G is the partition, so the labeling of the nodes. The nice thing is that actually that makes things even more twisted, is that modularity itself as a null model is defined with respect to a null model, which is exactly what this term here indicates, because basically it compares the number of edges that you have inside the cluster with the expected number of edges that you have in a randomization of the network that preserves the degree sequence. It's actually the configuration model that I mentioned before. So modularity uses the configuration model to define the baseline, which is given by this expression here. It's actually a very easy exercise to show that this is exactly the expected number of edges you would have inside clusters generated by the configuration model applied on the initial network. So if MC is sufficiently bigger than this, then the cluster is significant. So the bigger the difference, the more significant it is. And overall, the score is going to be larger. I'm not going to say much more about this. I want to just introduce the measure. This is an equivalent way to write it, which makes what follows a bit easier to follow, hopefully. It's the exact same expression, only instead of having a sum over the classes, I have a sum of the edges. And now this is the adjacency matrix. And this is this Ki, Kj divided 2m, which makes explicit the connection of the measure with the configuration model, because this is exactly the expected number of edges between I and j in the configuration model, as I told you earlier. And the sum is over all edges which are in the same cluster, which is why you have this Kronecker delta here, because Gi and Gj must be the same for this edge to give a contribution. Otherwise, it gives contribution 0. So it gives no contribution. So the configuration model is the baseline of modularity. And therefore, if you want to compute the significance of the maximum modularity that you obtain when you apply, for instance, some In's algorithm on a data set which is not too large, because otherwise it doesn't run, you have to use this model and do the exercise that I showed you before. You create a baseline distribution, and then you compute the p-value of the actual maximum modularity measure on your system, with respect to that distribution. This thing has been proposed 20 years ago, but not many people do that. People still today say, oh, it's bigger than 0.5, that means it's modular. Smaller than 0.3, it's not modular. But this is nonsense, because it really depends. If the network is sparse, modularity can be quite high, especially if the system is large. And most importantly, modularity can be very high, even if the network is sparse and random. But a random network should not have communities, right? So as the number itself does not tell you if you are clusters or not. You need to make a significance analysis. A significance analysis is the basis of this. We found this problem, that I'm going to mention shortly, just where we're trying to assess the significance of modularity in brain networks. And then we found it everywhere else. And then we found that it's not only for modularity. So it was a progressive escalation of things that I'm going to describe next. Okay, talking about networks, I mean, this is a slide that I added yesterday. I don't like to talk about this network very much, because even though it's super famous, it's probably the most famous social network that people use, definitely the most famous in this business and in network science. So much that there is an award, titled that I held for a year, 2 years ago. It's a social network of people attending a karate club in a US university. The Zachary Karate Club was put together in 1977 by Wayne Zachary, a sociologist that never would have expected that many years later this data set would have become so popular. Actually, I know the story now. Michelle Girvan told it to me before. When they published the famous Girvan-Newman paper, they had to choose a bunch of algorithms. They wanted to use the Southern Women data set, which is super famous in social network analysis, very small. It's actually bipartite network because it connects women and some women of some famous families and parties and events that were attended. But they didn't really have a clear ground truth there. And besides, there was this mixture, right, of women and events. And then eventually they found this one. And since that, the number of citations of this data set, of the paper, where this data set is compiled and described, has been skyrocketing. So basically what happened is that, and coincidentally, during the observation period, that's what makes these things very unique, there was a disagreement between the instructor, Mr. High here, number 0, and the president, 33 here, which led to a fission of this group of people into 2 different karate clubs, with the closest people to the instructor following the instructor, and the closest people to the president following the president. And then this thing has been used, and it's unfortunately still being used by some people, when testing clustering algorithms, and with the goal of separating the people who went with the president, which are the orange nodes here, with the instructor, from the people who went with the president, based on the structures, just showing that indeed there were 2 groups that even though they were merged because they were part of the same entity, the original karate club, indeed instead they were kind of distinct within the network. I'm telling you that because if you do this significance exercise that I told you before, if you compute the maximum modularity of the Zachary Karate Club, which is actually one of the few cases in which it is exactly known, and there's this red line here, and you compute the null model distribution that you obtain by randomizing the network, as I told you, configuration model, you scramble the edges, preserving the degrees of all the nodes, you get this distribution. Actually, you get a p-value of 0.07, which is marginally insignificant or significant. And in fact, actually, I wanted Timo to write something about this and say, why do you waste all your time on this network and so on, given that it doesn't even have a community structure? Probably. Anyway, this is just an aside. This shows you different distribution, different configurations. So this would be a modularity value corresponding to this partition. This would be the best partition, which is interesting, is in 4 clusters and not 2. And this one is the ground truth that I told you before, the one with the orange and the blue nodes that you've seen before, which is lower than that because it's not the maximum. In fact, actually, the ground truth is not significant at all, as you can see here. We can easily find random, partitions in random graph, in randomization, which have much higher modularity than this. But anyway, this is an aside, since you may remember. It's not the main point here. But this is the exercise I'm going to do. I'm going to assess the significance of modularity to start with, but then also of other quantities. And we'll see what happens if I change the scale. That's the only thing, that the scale, this multiplier, this constant. So I say, I was holding this award. This is a picture taken in my living room when I had it. Now it's given by somebody else. And I say, after what I showed you, maybe this could be a good solution for the award, just to get rid of it altogether. But now the question is, this network is not weighted. So how do we extend this whole framework, so the significance assessment of modularity in this case, but also other measures, including the ones that I already introduced, clustering coefficient and eigenvector centrality, to the weighted case? So how do people do? How did they do it? How did they do it so far? The answer came pretty early. This is a classic paper by Mark Newman, who was my big idol inspiration, who was also at the conference last week. In fact, I have a picture of Girman and Newman. I don't know if you follow me on Twitter. It's the picture of Girman and Newman. I was also in the picture. So this is the paper in which Mark Newman extended some concepts from the unweighted to the weighted case, including his own famous algorithm, the Girman-Newman algorithm, and the modularity, which actually was just introduced in the same year. So a couple of months after they introduced modularity in the Newman-Girvan paper, which followed the Girvan-Newman paper, which was a long version of the Girvan-Newman paper, he also proposed how to extend the measure to that. Most importantly, I would like to attract your attention on this sentence of that paper, which is the key of everything. And it looks extremely reasonable if you think about it, until it's not going to be. Every edge of weight n is replaced with n parallel edges of weight 1 each, connecting the same vertices. So it establishes a link between weight and structure. It says weight eventually is just a different form of structure. You can break it down into multi-edges. This is the problem that generates the issues I'm going to show you. And of course, like I said, it was 20 years ago. For some reason, it was. But it looked very reasonable to me. So for instance, in this case, if this is a weighted network and this is a ledge with weight 3, instead, the interpretation would be that you have 3 mini edges of weight 1. If the weight is not integer, it suggests to discretize it. You multiply everything by a constant, and that's how we realized that there was a problem. You multiply anything by a constant so that eventually everything becomes discrete. So if you have a comma and 3 digits after the comma, I multiply by 1,000, and then I lose the comma, right? Everything is discrete. And then I do this exercise, and then I can divide everything by the same scale at the end. It looks very intuitive, and it was intuitive to me until 2 years ago. Except it is not. Eventually it leads to this problem that I'm going to show you next. In the same paper, then, based on this concept, it trivially extended the modularity to the weighted case. And this is actually a very natural definition. This is the unweighted case. In the weighted case, you have, instead of the adjacency matrix, you have the weight matrix. Instead of the total number of edges, you have the total strength, or the total weight of the edges. And instead of the degrees, you have the weighted degrees as ISJ. And actually, I have nothing against this expression. The rest is the same. Interestingly enough, and that's good, now that I defined that in the weighted case, modularity is scale invariant with respect to my definition, right? If I multiply my matrix by A, and now that I have an expression for weighted modularity, I can do that. I put W prime here. What I'm doing is basically multiplying this one by A, this one by A, this one by A squared, because each of them is proportional to A, and this one by A. As you see, at the end, you get the same thing. Please?
I don't think it is scale invariant because we normally use it with the gamma.
Oh, okay, no, right. I'm talking about, let's forget about the gamma. I'm talking about the expression. And what I mean by scale is just multiplication by the constant of the weights. Yeah, okay. Right. That's a structural scale. I'm talking about really like the unit, right? So like I say, forgive me the semantics, and some people also, when I gave this presentation in front of Laszlo Barabasi and Santo last year in Boston, they didn't like the expression, but I think they understood the problem, and actually they agree that it's a big problem. So that's what I mean. The scale invariant means this. I multiplied by A. So there is no resolution parameter here. But the problem will be the same. Once the resolution parameter is the same, like you fixed, then the measure does not depend if I multiply the weights by a constant. And that's exactly what I'm showing here, which is good. That means that if I multiply everything by a constant, all the edges by the same constant, I'm going to get the same communities, I'm going to get the same partition having the same maximum modularity. And each partition will have the exact same modularity in the two networks, which is good in principle, right? So that's no problem with the measure. So each partition is the same modularity for every value of A, and the maximum modularity in particular is the same, which means that the communities will be the same, which is great. It's exactly what you would expect in a consistent formalism. But now, how do we extend the configuration model to the weighted case? That's key. Now, following Newman's lead, in which the weights are basically multi-edges here, I can do the same exercise. I just break these edges here, and then I combine them pairwise. It's a very simple strategy. This is called the weighted configuration model. And in principle, it's exactly what is used behind modularity's formula. This SI/SJ divided by 2W is explained exactly by this mechanism. So it's super simple, super intuitive. And that's actually makes things even more interesting next. This is called made the configuration model. As far as I know, the first expression came from Serrano and Borgugna, 2005. We're talking about prehistory, WCM. And also in this case, like in the unweighted case, the distribution of the number of edges between any two nodes is a Poissonian, with average SI/SJ divided 2W instead of KI, KJ divided by 2M. It's a natural extension. This is all square. This is all 100% accurate. And this is the same Poissonian we've seen before. There could be a little problem with that, right? Because if I multiply by a scale, you see this expression here grows linearly with A, so at some point it can become bigger than 1, and then you lose the meaning as a probability. But like I said, the real meaning of this ratio, SI/SJ divided by 2W, is actually the expected number of edges between I and J in the configuration model. And as such, this number can be bigger than 1. All right, so this is what I'm going to do. And that's where the problem is going to emerge, finally. So prepare for the big coup de théâtre. I don't know what time it is. Perhaps I should know. But we're not far from. Sorry? Oh, I'm sorry, it's right. Yeah, okay, perfect. Yeah, so I have plenty of time. So what I'm going to do, I'm taking my network, whatever. I'm going to show you 3 examples, but we did many other examples, the result is general. I'm going to compute the maximum modularity, and I call QM. Then I do the randomization, I do configuration, the weighted configuration model, the way you've seen it, by connecting stubs. And I create my baseline distribution. And then I compute the p-value of that. Then I multiply everything by a scale, by the same scaling factor, A, and I do the same thing. And I want to see if anything changes. Modularity is not going to change, as I just showed you. The value of modularity, maximum modularity is not going to change. So QM is going to be invariant, because I just showed you. Let's see what happens to the assessment. This is what happens. These are the baselines that you obtain if you use different scaling factors. This is the best modularity, which is scale invariant. This is the one of the ground truths, which is the modularity of a specific partition is also scale invariant, doesn't change with that. But you see that the baseline is moving to the left, and it's shrinking. So basically that means that if I choose an A which is large enough, then my modularity becomes significant. Any modularity becomes significant. So this is the problem. The p-value depends on the scale because the baseline distribution is not scale invariant. So this is what we discovered, which was shocking. We thought there was a mistake in the code, and then realized instead, when you have 2 years to think about stuff, that instead it makes sense. And I hope that I can convince you why it makes sense. So you see, of course, you're getting far away from this line, which is steady because it does not depend on the scale, and eventually everything becomes significant. And this is actually, this is another thing, just to push it to the limit. This is an Erdős-Schrödinger random graph, very small. Just to have fun with that. That would be then the best partition, the modularity of the maximum modularity that you get on that. This is the baseline that you obtain, and indeed you see that this one does not have a small p-value, which means that indeed this is a random graph, right? But if I multiply, if I turn my network from unweighted to weighted and multiply by a scale, then you see that again, the baseline moves to the left, and eventually even a partition in a random graph becomes significant, which is nonsense. So this is one of the paradoxes that you get from that. This is just because I'm using the weighted configuration model. And most importantly, because I take the assumption that Newman made some years ago that weight equal multi-edges. Everything comes from there. All right, then let's take a couple other examples. This is the World Trade Network that I showed you before in one of its many versions. This was actually the original one, using the original currencies, hundreds of millions. If you plot, so if you report the exchanges in tens of millions of dollars, you get this baseline distribution in millions of dollars, in hundreds of thousands of dollars, in tens of thousands of dollars, if you keep moving to the left. And then eventually what was a non-significant partition here becomes significant here. So it's at the same time significant and not significant, which is of course contradictory. Please ask me at any time. This is a conversation. This is a work in progress. I've been saying this for a while already, but I think it's important because it's kind of more unusual, and we're not done yet. This is a brain network, same thing. Now, what really happens, and what seems to be common in all these cases, is that the standard deviation of the null model distribution shrinks to 0 as you increase the scaling factor. So this is the observation. And interestingly enough, it doesn't just change randomly. It changes in a very specific way with the scaling factor A. In fact, the standard deviation of the null model distribution, in this case of modularity, for any network goes down as the inverse square root of A. When we found this, we thought, oh, this is cool. It's the same thing. And let me show you where it comes from. It will be this blue line here. The other things are, just to see how dense the network was as you increase the scaling factor and how big the giant component is. And the values are reported on this axis here. This would be for standard deviation of modularity. So it goes down to 0. And this, as you can see, we didn't put the fit here, but this is an inverse square root. This is for the brain. This is for the trade. You found the same thing. If you take any network, you're going to find the same thing, which is interesting, right? So it's not system dependent. It has universal scaling. That's the first general thing. So universal scaling of the standard deviation as a function of A. Second universal thing, this thing that I showed you is not only valid for modularity. The two other quantities I introduced before, just because we have time to play with them, but I'm sure that there are other cases. The weighted clustering coefficient, a la Saramaki et al., the non-trivial one, and the maximum weighted eigenvector centrality, in which you just take the maximum value for the network, because otherwise you have a vector, right? Vector centrality is a vector, because it's a centrality distribution. But if you take the maximum value, then you have just a value that characterizes the whole system, although it will be eventually the eigenvector centrality, the entries for a single node, but it can characterize a network at large. If you do it, you see now this is for the clustering coefficient, standard deviation goes down the same way. Here there are some fluctuations here, but we've seen it also in the toy model. I think we need just more statistics in here. You're going to see some noise at some point because we have not run things long enough, but we haven't found exception. This is for the maximum eigenvector centrality. So the standard deviation of the baseline distribution of modularity, maximum eigenvector centrality weighted, and weighted clustering coefficient goes down as the inverse square root of the scaling factor. So it doesn't depend on the measure, it doesn't depend on the network. So it's even more universal than you wish. So physicists like Fabrizio, they love universality, but sometimes if you exceed in universality, it starts to be puzzled, because then there must be some simple explanation behind that. Now, I don't have really an explanation, and this is the reason why I offer co-authorship here. I mean, not like a rigorous one. We're still chasing one. Let me give an argument, which is really hand-waving, but it works well, and it helps to understand how we can fix this, which is the following. I assume that the variable that I'm considering is a linear function of the edge weights. That's certainly the case of modularity here. This is the variable. Everything else is fixed, because for my input network, Si and Sj are two constants. The strength of the system that is given to me. The only thing which is random is this thing here, which is generated by the randomization of the network. But Si and Sj are preserved. W is preserved because it's the sum of all Si divided by 2. So the dependence on the random variable is only here, and it's linear. Now, let's look at this one, and then of course there is a ratio by W, which scales linearly with A, right? The total weight scales linearly with A, obviously, no, because you just increase, you just multiply everything by Now, I remind you that Wij is a Poissonian distribution. Also in the weighted configuration model, the expected number of edges, or if you want, the expected weight between I and j follows a Poisson distribution. We are sticking to the case of integer weights here. For continuous weight, we can use something else, and we can discretize, but in fact you cannot discretize. I'm going to give a recipe for both things at the end. But let's assume it is discrete, because a Poissonian distribution is a discrete distribution. Now, the standard deviation of the mean of a Poissonian distribution is the square root of the mean. This is a characteristic of the Poissonian distribution. So the mean is SI divided by 2W. This one scales like A, because it's a linear function of A. So you have a square root of A. But then I have to divide by this to derive the standard deviation of modularity, something similar. I mean, talking about scaling here. Of course, I'm not talking about constants, multiplication, and so on. We're not talking about the behavior with respect to the dependence on A. So the standard deviation then is approximately the ratio of the standard deviation of the random variable divided by W, which also scales with A. And if you make this ratio, you get A to the minus 1/2. That would be my rationale. It applies certainly to modularity. I'm not sure it applies to the weighted clustering coefficient, even because you have those cubic roots. But at the end of the day, even the weighted clustering coefficient at the end is still linear function, effective linear function, because you're multiplying 3 cubic roots. But like I say, I mean, we're still working on that. This is one of the missing things before we can finally push this thing out. If you have ideas, now that I told you how general the thing is, more precisely, text me. We have my email. You can easily get it from Pierre, Mario, or me. Talk to me during the coffee break. You can easily find it on my website. And let me know what ideas you have. This is really a mathematical thing. So this is Mathematics Institute, so it's probably the right place to solve this problem. I just didn't have enough time to sit down and think about this. The story has changed multiple times as we discover new things, in generality, and so on. So that's the reason why it took me like 1 day just to adjust the original presentation into this one, because at that time things were even more rudimentary, preliminary. We didn't think there were other measures other than modularity for which this thing would holding, and said it's a very general problem. So my conclusion is that this peculiar inverse square root behavior is due to the fact that we're using the Poisson distribution, which is a consequence of the fact that I'm doing configuration model on these multi-edges, which are the weights, according to Newman's hypothesis. Now, what happens if I change the distribution? Can it be that I solve this problem just by simply changing the distribution? Instead of sampling from Poissonian, when I create my randomization, I don't sample from a Poissonian, I sample for something else. What could be a good distribution to solve this problem? How about the exponential one? In the exponential distribution, the standard deviation scales exactly like the mean, not like the square root of the mean. If you do that, then you expect that the standard deviation will be indeed scale invariant. Is that true? So this is, again, we need to run it more times, but you see here, we don't have orders of magnitude anymore on the y-axis. The numbers are comparable. We need to run it a few more, but especially for the toy models, modern networks, these things is really nice and flat all throughout the whole range of the scaling factor. This is the scaling factor. It's called it average strength because it's computed with respect to that network, but it's just, it's proportional to A. And the same thing for the, this is for the modularity, this is for the clustering coefficient, this is for the eigenvector centrality of the Zachary-Karate club. But if you take the brain network, you also obtain, you see also here how tight these numbers are with respect to each other. Like I said, again, we need to run things more often because there is a lot of noise. These are real networks. And the same here, you see that basically things are fairly scale independent. World train network, the same thing. Okay, so I'm almost at the end of this, which is good. I think we are on time because I also want to get questions from you if you have some. But there are some issues when using the exponential distribution. I mean, this is the final thing. 2 problems. Problem number 1. First of all, the exponential distribution is continuous, where we're talking about integer weights. And it's not a detail, right? So how do I do it if the weights are integer? I can discretize the exponential and use a geometric distribution, which is, as you know, a discretization of an exponential. The problem is the geometric distribution kind of interpolates between a Poissonian and an exponential. The geometric distribution becomes kind of exponential in the limit in which the probability goes to 1. So what happens in this case is that if you do the same exercise using the geometric distribution instead, like in this case, you get scale invariance only asymptotically. You have a transient, because what happens is that if you have a discrete distribution and the constant is low, eventually you're going to get a lot of zeros out of this distribution, right? So that's the same thing that happens with the Poissonian. If you get a lot of zeros, your network is empty. You don't have many edges. And the lower the constant, the more empty the system is. So it becomes very different from the original one. So it's a transient that it's better to neglect. But once you get enough statistics there, then you get a more or less stable behavior. And I just give you this example. So basically, in this case, if you use integer weight, just use the geometric distribution and focus on the asymptotic plateau for the significance assessment, because that is scale invariant after a transient. That was problem number one. So discrete weights, use the geometric distribution. Continuous weight, use the exponential distribution. The problem is that if I use the exponential distribution, suppose that my weights are then continuous, like real. The exponential distribution is always going to give a number which is non-zero, which means that basically your randomizations are going to be weighted networks which are fully connected. But if your input network is sparse, like most input networks are, except world trade, in which every country more or less exchanges goods with every other country, it's very dense. But most networks in the internet, the web, food webs, social networks, and so on, they're sparse networks. It's kind of difficult. I mean, and we can negotiate, because at the end you choose a new model. So it's not that. But of course, at the other hand, it shouldn't be too arbitrary. You don't want a randomization which generates systems which are too different from the original one, because ideally we would like to keep the two things as similar as possible, while randomizing instead some aspects of the structure. So basically, what happens if you use exponential distribution is that you start with a sparse graph, and your random networks are all going to be fully connected. And because of that, you can expect, since there is this big discrepancy, especially if the initial input network is sparse, that everything becomes significant after a while, because, I mean, eventually you're going to compare things which are quite different. So it doesn't look ideal from this point of view. So what is then the final solution? Separate the weights from the structure. So basically, contesting the original assumption that Newman made 20 years ago, that weights are just, can be embedded in the structure, can be reformulated as a structural feature. This is the solution that we propose. And actually, interestingly enough, as you start reading stuff and so on, you realize that there were ensembles which preserve structure and weights already many years ago. And until recently, people have still been playing with this. These are two papers that I recommend. These are the first two papers in which by Bianconi and then Mastandrea et al., Garlaschelli and so on, in which they propose, but not to solve this problem, for other reasons, just to increase the similarity between the randomizations and the network that they are supposed to represent or to scramble. So in this case, what you do, you preserve both the degree sequence for getting the weights, and then once you do that, then you distribute the weights on the links that you generate through the randomization. So basically, at the end, what we've been doing, mostly connecting the dots, because eventually these things were already out there, and the way we are implementing it, and you can choose otherwise, small modification, is you do configuration model on the initial network for getting the weights, and then once you get your random configuration, you assign the weights to the edges, sampling either from an exponential distribution, if your weights are continuous, non-integer, or from a geometric distribution, if your weights are integers. So this would be our final recipe. If you do that, and again, we have to run these things more often and so on, but you see how close these numbers are with respect to each other, you get your scale invariance. So this is a summary. Current null models for weighted graphs are unsatisfactory. The weighted configuration model is fundamentally problematic, and although it looked very intuitive, because if you use it to assess the significance of various measures, not only modularity, but also the weighted clustering coefficient and the maximum weighted eigenvector centrality, this assessment depends on the unit that you use to measure the weights, against the intuition and the expectation that this rescaling should not change fundamental results of analysis, of any analysis. And the reason lies in the fact that weighted edges are multi-edges. This is the assumption behind the weighted configuration model. This is not true, because it clashes against this very intuitive property of scale invariant, unit invariant, however you want to call it. The observed scaling, the a to the minus 1/2, is due to the fact that the weighted configuration model comes with a Poisson distribution. And the standard deviation of the Poisson distribution happens to be the square root of the mean of the Poisson distribution. But if you choose another distribution, like the exponential, you don't have this problem, and I showed you that numerically it seems to be working. Finally, the exponential is a continuous distribution, and it generates fully connected weighted graphs, which are not realistic. That's why we don't simply replace the Poissonian with the exponential, because in principle you can do just that. If you want just to scale invariance and show it to you, I just replace the Poissonian with the exponential. But then the problem is that then you get always these fully connected graphs, which really look different from the original ones, which is usually sparse one. And that's why we move to the final frontier and the final message, which is separating topology from the weights. And in this way, actually, what you generate is fairly similar to the original one, and it does not have this problem of densification that you would get if you use a continuous distribution, not necessarily the exponential, to randomize the weights. That's all. Thank you.
Thank you very much for a very stimulating talk. Any questions?
Fabrizio?
Thanks a lot. Yeah, so thanks a lot. So the main problem is, so your main message is that the null model was wrong.
Yes.
It's not a property of the network.
No, no.
Right?
Or modularity. Even modularity, this formula is compatible
Right,
with this thing.
So
Yeah,
it's
likely.
really a problem of the null
Model, yeah.
null model. And in fact, I mean, you mentioned at the end, there is all this approach which is called zero augmentation or zero inflation for null models, which exactly do what you mentioned at the end. So which is decoupling using the configuration model for the degree and using any distribution for the weights conditional to the link. Okay, so it's a conditional probability. So you can use, for example, you mentioned exponential and Poisson, but of course you can use gamma, you can use negative binomial, you can use log normal, you can use anything which actually fits better with your data, because at the end, I mean, maybe you use exponential distribution, but the weights of your network are not exponentially distributed. So it would be another type of misspecification. Maybe it's better fit as a log normal. So you can do exactly the same approach, but using any distribution, I think, right? There is no reason to use the two distributions that you have. You simply have a conditional distribution of the weights, the fact that the link exists.
Yeah, you have, of course, that level of freedom when you choose a new model. But I mean, based on our experience, unless you use exponential, I mean, I don't know, but there may be other cases. We tried a few other things. The exponential, which is actually the maximum entropy randomization that you make, which is also why it's appealing.
Depends on the constraint. It depends on which constraint you have. Yeah.
Yes. It's the only one that preserves scale invariance that we found. So, I mean, if you use the other distribution, you're probably gonna break scale invariance. So this could be actually...
Sorry, when you are continuous, you don't care about scale invariance, no, at the end.
No,
so
it's...
scale invariance enters when you have the problem of discretization.
Right. No, but you can still, I mean, even if it's continuous, you can still change the unit, right?
Right.
So, yeah, this is the problem. Actually, this is interesting what you're saying, because in principle, this is true. I want to make one step towards realism, so I use the real distribution of the weights that I get in my system. But more often than not, this thing is not going to be scale invariant. I mean, it's not going to generate a scale invariant null model with respect to this. Actually, let's talk about this, because I'm sure that this...
Tomorrow we'll be using a zero-inflated model with gamma distributed weights.
Yeah.
Because this fits better interbank.
Yeah, sure.
But so, and I didn't talk about the scale invariance issue for continuous.
Yeah, but I mean, like I said, I mean, you wouldn't, I mean, I don't know, it's certainly not a general thing. The nice thing is that the exponential solves the problem, and the exponential happens to be the maximum entropy, randomization that you can get, which of course is not the only one. But it's appealing just because people like to randomize as much as you can. And this actually stems very nicely from the formulas that Diego Galascelli et al. Made. In fact, Diego at some point wrote something, he said, we realized that if you use the weighted configuration model, there could be the randomization depend on the unit that you choose to measure. But he didn't elaborate. So there never been. I also talked to Tiziano Squartini at the conference with whom he did these things. And he said, oh yeah, we didn't really elaborate. So he was interested, as you remember, in this thing. But unfortunately, you see, even the geometric one, unless you go to the asymptotic limit, it's not really following that, because in this case, of course, it's a discrete distribution. But not every continuous distribution respects this. We didn't find anything other than the exponential, but of course, we cannot claim that we tried all the distribution. Yeah, so that's how tricky the thing is. Because I think that it's very natural to assume that there is scale invariance, right? Because I mean, that the fact that that you use dollars or yen and so on should not really change any fundamental questions. But instead, for these basic models, it does. I think there is a question. Oh, sorry, there was a question right there. Thank you.
So
Thank you for this.
you used the Karate Club data set, which makes total sense. I'm curious whether anybody's been applying these techniques to financial networks of any variety.
You mean, in my opinion, is that everybody should apply, should do significant studies on any network, so including. And the reason probably why I'm talking about this in 2024 is the fact that people not doing this, because otherwise they would have found this right away. What we did, we had a brain network, so completely different domain, but the weights were not continuous. And then I say, I remember the trick that Newman suggested. Let's multiply everything by a constant. We scrambled thing, and then we divide the weights, and then we realized that the results was changing with the constant. And that's when we started to say, how is it possible? Is there a mistake in the code and so on? Until, now of course everything is very intuitive, but it took a long time to get that. So basically the answer is that you have to use this everywhere, and you're going to find this problem everywhere. I did the example of the world trade to also warn especially you, because you need to choose a unit, right, to quantify the exchanges, the transactions, and so on. And even if you don't change a currency, if you report your results in millions of dollars, thousands of dollars, and so on, it shouldn't change. Something as important as significant. I say, cannot tell me that if I use thousands of dollars, the thing is significant. If I use millions of dollars to quantify the exact same thing, the thing is not significant. I don't accept that. I think we should not accept that, and that's why we should do this maximum entropy thing that I suggest. Please, Mario. And also there was a question in the back.
When you go from the unweighted to the weighted case and you want to follow the Newman idea, then the probability distribution should go from Poisson to binomial. And this would also explain why, if you increase alpha, the skewness increases in the distribution.
Why would that, and that would move the distribution of the number of edges between two nodes is Poissonian, whether the network is weighted or unweighted. If you just extend the configuration model the way Newman suggested with the multi-edges. If you think about it, just increasing the number of units that you have in your system, but the procedure is identical. It's just combining pairs of stubs. So.
Yeah, but now you connect one among many.
Sorry, one?
You connect one among many. If you have many edges,
yes,
you have just one. You connect just one among the many that you have.
Well, you have to connect all the pairs, right? Eventually you have to connect the network. So, let's talk perhaps about this, because I'm not sure I understand. Yeah, Samin? But I think there was a earlier question there. But okay, the microphone is closest to Samin, so I think it's right. We have time. There's a coffee break, so.
I have a very dumb question.
I see.
Is significance scale invariant?
Yeah,
or should statistical significance be scale invariant? So just think about a two-sample t-test. We, let's say, run an experiment between a treatment group and a control group, and consider two scenarios. In one scenario, everything is multiplied by 100. The number of mice in the two groups multiplied by 100, and all the results by 100. Should everything in terms of statistical significance remain the same? This is a question also for statisticians in the room. I don't know the answer.
You can imagine how many deep conversations we had between ourselves and also with a few people who know about this whole idea. And there are two parties. Not even two parties. There are situations in which we have a unit and a situation in which you don't have a unit. If you're talking about contacts, like a number of phone calls and so on, you have a unit, right? So in this case, you expect that if you have more of this, then eventually this thing is going to affect it significantly. But in a situation like, I don't know, the world trade, for instance, in which you have in principle a continuous, range of values, and it can change where you are based on the currency that you choose, which you should be able to choose. I don't see a unit there. In case of distances, so, eventually, and this is one of the things we'll have to go through when we write the paper at some point, hopefully this summer, And this is one of our, actually, Philippe was telling me, there are situations in which the units is well defined. I mean, it's a kind of unbreakable. And in that case, actually, then you would see that indeed the significance would change, if you increase the statistics. Because actually what happens here is that if you increase the scaling factor, if you do this equivalence, weight equal multi-edges, you're going to have billions of these multi-edges. So because of the randomization, eventually you're going to stick with configurations which are basically identical. That they differ very, very little from each other, which is why the standard deviation goes to 0. Because you have all these units, right? So you have basically infinite of these multi-edges, of these mini-edges and so on to combine, and then eventually everything gets frozen. And there is no variability. And that's why everything which falls outside of that value is significant. But in some cases, yes, I mean, I'm willing to negotiate that there are cases, especially in, I don't know. But even if you say, I give the example of the phone calls, I can say, yes, I mean, number of phone calls, but I can also say how long we were on the phone. And then you are back to my case. Minutes, hours, seconds, milliseconds, When you have a continuous thing, somehow the units shouldn't matter. So if it's instead of number of contacts, it's duration, then, so there are certainly settings in which very naturally the thing is believable, that, it shouldn't be scale invariant. And some settings in which maybe there is a unit which people would agree upon. And the moment there is a unit, then, it depends on the unit, obviously, somehow, which is exactly what we find. Because in general, the message that in general it depends on the unit. Only in some cases, it's hard to believe that the choice of the unit should make this type of difference. Like in the trade and other things, or these things with duration, time, with distance, space, and yes, thanks a lot. We talked a lot about this. So, please?
Yeah, so
Thank you. Sure.
So maybe just reinforcing this comment, and by the way, a brilliant way that you presented it, just like an Agatha Christie.
I tried to.
So yeah, I got to your answer one bullet point before you presented, so the last page of the book. So that's
that was the intention.
And the answer is exactly this: breaking the structure from the weights, right? So it makes sense in one network if you're not randomizing, just to say that 1,000 trades of $1 million is the same thing as 1,000,000 trades of $1,000.
Yes.
But in reality, if you're now going to compare to an ensemble, you're going to have to randomize and now rewire this 1,000 trades or 1,000,000 trades.
Precisely.
And that's going to change the baseline, right? So,
at the end, it's super intuitive when you explain it like this, but believe me, it took us months to get there, because at the beginning we thought there was a mistake and so on, because we didn't want to go against the giant. Actually, I mentioned Mark Newman that there is something I wanted to discuss with him. He doesn't know about this because there is, aside from this couple of presentations, there is no technical reports or preprint or anything that is ready for that. And like I said, I still don't have the explanation of the inverse scaling. I mean, I don't have a general argument. I mean, I just made the argument when you have a linear dependence, which naturally leads to the fact that if you change the distribution like the exponential, then you don't have it, which is true. But I don't really have a proof yet. So this is still missing, and this is one of the things that's still keeping us from finalizing everything in writing. So think about this. This is a general thing. It's so difficult in 2024 to talk about really deep theoretical questions about this discipline, because now it's mostly on the application side. Of course, there are still methods to be developed and so on. And this is a very old story. Like I say, everything started with the 2004 paper, Mark Newman, where he extended things from the unweighted to the weighted case. And now we know that this is not the right thing to do. So. And like I said, there is not that there is a single recipe, but just decouple the two things. And if you want to keep the weight distribution of the regional system, I think you may have surprises. You may find out that the baseline in this case would change with the scale, which is disturbing. But let's talk about this, because I know Fabrizio to do these things. I know many other people. I did myself in the past, but at that time I thought I could change things as I wished. Now I'm not so sure anymore. Final? Thank you.
Great talk. So if we take the adjacency matrix of a weighted graph, and then if we randomly rewire the elements, as in randomly scramble the elements of that matrix, we would get a random graph with some properties intact. And then I'm not sure about other properties, but we have tested it for something, and at least for eigenvalues, this has some. The original graph has some differences from this new matrix. So like we can make out the significant eigenvalues from just randomly scrambling the matrix of a weighted graph without considering it as a multi-graph. I don't know if...
So you're saying that you propose a randomization in which you're just basically shuffling the elements of the matrix?
Yes, of a weighted graph.
Of a weighted graph. I mean, of course, if you do that, I mean, of course, it's, like I said, we can be flexible about the type of, but if you do that, of course, I mean, that basically, in a sense, fundamentally changing relabeling the nodes, right? Because so.
Not relabeling because we are not doing it simultaneously, the rows and columns. If we do rows and columns simultaneously, then it's like relabeling the nodes. But if we just do rows first and then columns first without any relation between rows and columns, then it's not relabeled.
So if you do it first, I mean, I don't see how they become it. But then don't you get the asymmetric matrix at the end if you do that?
Yeah, but still it can preserve eigenvalues and like it can give us some information about significant eigenvalues even if it makes it directed.
I see.
So
yeah, let's talk about this. I mean, the problem I have with this is because of course if you do it, just if you just do swap pairs or entries, what you're doing is basically just changing the labels of the nodes, right? But if you do it in this sequence, I think you're generating generally a directed graph. But let's talk about this. I don't know exactly what I mean, the good thing is that, you can propose your own thing. The point is that, we should have some sort of, guidelines to follow. And I don't want to give up scale invariance because I believe in it. And maybe it's not a super general because there could be cases in which you can justify that indeed you have a unit. And once you have a unit, then the result depends on the unit. But the fact that you impose this thing, because I believe in that, constrains very much the set of choices that you have. So after this, and also perhaps also after the discussion we had with Fabrizio before, it's probably not so easy to find alternatives to, for instance, what I'm proposing here, which respects this constraint, this need that I have. But we are at the beginning of this, so you're happy to follow up. And please, if you have a solution for the inverse square root scaling, like a general one, and not today, but whenever you have it, just please, we're going to add you to the paper and I'm going to make a contribution. Thanks a lot. Thanks for your attention.
Thank you very much.